Okay, just quickly, the agenda for today is that we're diving into the ocean component of CESM. 3 different lectures on different aspects of the ocean model, which is brand new in CESM 3. And then for the lab, we are going to go into name lists and code changes. So you're going to start looking at the specific name lists of the different components of the model and do some source code changes to the simulations. We'll have another meet an expert at lunch, so double check your assignments, and then we'll follow the same kind of process in the afternoon, lab check-in, daily debrief. Just as a reminder, again, the official lab of the day is Namelist, troubleshooting, and sourceMods. But of course, this is a self-paced lab, so if you're still working on basics from day one, or if you're still working on the simple XML modifications, that's perfectly fine. You can ask questions about any of the labs today. And so I guess that's all, unless anyone has logistics questions about today. Okay, then we can go ahead and start with our first lecture. Gustavo Marquez is a scientist in the ocean section.
Good morning, everybody. Welcome to the most important component of CSM. And why is the ocean the most important component of CSM? Let's see if I can convince you. Who knows what percentage of the excess heat since the Industrial Revolution has been absorbed by the ocean? 90. 90, yes. Now, they say 93, the IPCC report says approximately 90. Very good. So that's one. The second one, how much of the CO2 that's being released by human activities is absorbed by the ocean? 40? No, a little bit less. 25. Approximately 25%. So 25% the ocean, 25% the land. As the temperatures are warming, land is growing more stuff and is absorbing more, and then 50% in the atmosphere. So 90% approximately of the excess heat and a quarter of the CO2 is being absorbed by the ocean. That's why the ocean is the most important component. So every morning from now on, when you wake up, you have to thank the ocean for doing its job, because otherwise we would not be able to live on this planet. Okay, so let's move to the presentation if I can. Oh, looks like I got a little hiccup here. Chris is not asking to share, is not asking to mirror anymore. I'm good? Cool, thank you. All right, so my name is Gustavo Marquez. I'm a scientist in the oceanography section, and I'm also the co-chair of the Ocean Model Working Group for CSM. So a quick overview of this presentation. I'll go through like the general of ocean modeling considerations, some of the basics and the challenges when modeling the ocean. And then for the first time in the tutorial, we will be diving into MOM6. I was previously giving the lecture splitting between POP, which is the old model, is the Parallel Ocean Program version 2, which was used up to CSM 2. And then starting CSM 3, we've switched to the modular ocean model version 6. So 90% of the ocean model dive will be about MOM6. I will still mention a few things about POP just for comparison purposes. And then finally, I will end with some helpful resources. So we already discussed how much heat the ocean has been taking since the Industrial Revolution, and why the ocean has taken so much heat. And the primary reason is because of the heat capacity of water compared to the heat capacity of air. So to give you an idea, the top 3 meters of the ocean hold as much heat as the entire atmosphere stacked above it. And that is because, one, the heat capacity of the ocean is 4 times higher than the atmosphere, but also because the mass in the ocean, the amount of water compared to the amount of air, there's much more mass, water in terms of mass than air above it. So that's why the ocean is taking so much of the excess heat. So the first order challenge from a numerical perspective of simulating the ocean is the irregular domain. So this is a three-dimensional image of the ocean bathymetry focusing on the western North Atlantic. So you see the east coast of the United States, and then you see the continental shelf. Let's see if I can use my, oh, here you go. It's always a challenge to use this. No? Okay, well, I'm not supposed to touch, but I'll go close. So you see the continental shelf. Notice how the continental shelf width changes as you go through the coastline. In some places it's very narrow, in some places very wide. And then the ocean topography, you see the mid-Atlantic ridge. So there's a very complicated structure underneath the surface of the ocean. And then I'll play this animation on YouTube. And let's pay attention. So these are like surface currents. These are from a high-resolution simulation using the MIT model. But now we're going, again, this is the same region I was looking before, the eastern North America. Here is the Gulf of Mexico. Look at the eddies being shedded by this loop current that detaches every now and then and form these eddies that then go into the Gulf of Mexico. The Gulf Stream on the top, and now we're moving to the equatorial region, the North Brazil Current. Notice how the coastline is influencing how things happen. Now moving across the Atlantic, look at these eddies that get shedded by the Agujas Current. So those are the Agujas eddies, and they bring important properties to the Atlantic from the Indian Ocean. And here between Madagascar and Africa, how, again, the coastline and topography is controlling what the flow is doing. Just to give you a sense, so unlike in the atmosphere, where the topography or the bathymetry plays a role as well, but like here is way more influence because you're confined by these boundaries. All right, so another example of now diving into a comparison between ocean and atmosphere, and we'll look at temporal scale on the y-axis versus spatial scale on the x-axis, and these balloons are different processes. So on the bottom left are things that are very small and very fast, like capillary waves, vertical mixing, and on the top right are things that are very large spatially and very slow, like climate change, modes of variability, and so seasonal cycle. So if you use a typical, like this is the lowest resolution model we've built in CSM, like a 3-degree, nominal 3-degree, this is the green box. That's the kind of process that you can capture. So you can capture climate change, you can capture El Nino, seasonal cycle, but no, you barely change on the eddies, oceanic eddies, which is equivalent to the weather, like the cyclones in the, oops, just lost my. So the ocean eddies are equivalent to the weather systems in the atmosphere. So you barely resolve, maybe like right next to the equator. Now similar with the 1-degree model, which is our typical workhorse models, the ones that we use out of the box in the simulations, you can now go a little bit more, but still like you don't resolve eddies at all. And here is like the highest resolution we have, or for long simulations, approximately a tenth of a 12th of a degree. Then you resolve a significant amount of eddies, but not everywhere still. Okay, so the bottom line is like global ocean models simulate the climate. If you do the same type of exercise in the atmosphere, and now focusing on the typical workhorse resolution 1 degree, you simulate a significant amount of tropical cyclones. It's still not the, like, if you talk to a weather person, they say, oh, 1 degree is not enough to resolve cyclones. Yeah, it is not. You have to go much higher, but you can capture a significant amount of energy associated with them. And so the bottom line is, like, the global models used for as part of the atmospheric components simulate the weather. So in the ocean, we simulate the climate. In the atmosphere, the resolution is high enough to simulate the mesoscale activity, if you will. And here is an example on the left. So both of these maps are for the same date, our sea surface temperature for the same date. And on the left is 1/10 of a degree. And this is on the tip of Africa. Again, the Agujas currents being generated. And on the right is for a nominal 1 degree. So what is the main difference here? What do you notice?
Eddy resolving more on the left?
Yeah, so on the left, you're resolving the mesoscale eddies better. On the right, like they're completely gone. So what we need to do is the mixing associated with these eddies. Notice how there's orange being carried from one side to the orange to the other side. So there's water properties being carried by these eddies. And that is completely absent on the one on the right. So we must parameterize the subgrid scale turbulence associated with these eddies in a low resolution model. That is a lot of the business that we do is try to represent features that cannot be resolved by our model using parameterizations. And Peter Gent in the next lecture will dive more into this, the two most important parameterizations that we use. Okay, why in the atmosphere, like with the same resolution, you can capture more features compared to the ocean. That boils down to the Rossby radius of deformation. So this is a measure of the spatial scale needed to resolve mesoscale eddies. And in the way you represent the Rossby radius is the ambient stratification, capital N, times a typical vertical length divided by Coriolis parameter. And N, the Brun-Weishaler frequency, or a measure of stratification, is a function of the density change in the vertical. In the ocean, there's very little density change as you go from the surface to the bottom compared to the atmosphere. And that's why the Rossby radius of deformation is much smaller in the ocean compared to the atmosphere. So you would need much higher resolution to capture the same processes that you would with a lower resolution in the atmosphere. And this map is showing what is the typical grid resolution needed to resolve the first baroclinic radius of deformation, or this quantity shown above in the globe. And even with a 1/10 or 1/12, so the yellow part, you're not resolving everywhere. You still, if you notice that on the continental shelf, next to the continents, the red part, you need much higher resolution. So it's very, very hard to resolve the first baroclinic radius deformation everywhere in the globe. Okay, another challenge is the calibration time scale. And I'll give you two different ways of looking at this. One from a mixing perspective. So once the waters sink in the ocean, they form what we call water masses. There is very little mixing that happens from that point on. And this is why we can name the different water masses. And I'll show you an example in a few slides. But then from a mixing perspective, if you have a typical depth of the ocean, 4,000 meters squared, divided by the turbulent vertical mixing, 2 times 10 to the minus 5, that gives you a time scale of 20,000 years. So this is how long it would take for something to equilibrate once it goes into the ocean, like tracers and temperature, salinity. So it's very, very long time. So this is from a mixing perspective. We can look similarly from a dynamical adjustment perspective. So the phase speed of the Rossby waves crossing the Pacific, this is the the way we would compute this is the phase-speed relationship, and using values typical of the Pacific Ocean and mid-latitudes, it would take approximately 2 years for the Rossby wave to cross the Pacific. So much faster than the mixing response, but these things kind of, if you want to look at an equilibrium state, you would need the mixing to take place for the tracers once the water masses are formed. Another big challenge is the way the ocean applies mixing. So the schematic shows that near the surface, this is what we call this bottom boundary layer, you have a lot of mixing happening. You have the influence of the atmosphere, surface gravity waves breaking, the solar heating, wind, all of that. So there's a lot, things are well mixed within that top layer. And then you have a sharp transition, we call, depending on the property, it can be the thermocline, the picocline, so on and so forth, and where there's a big change. And then in terms of density, the ocean interior, then you have this well-defined isopycnals, which of this gray line represents an isopycnal. So it's a line of constant density. And then once the water is buried under the bottom or the top layer of the ocean, mixing occurs along isopycnal. So those are these blue arrows. Very little mixing occurs across. So that red arrow in the schematic is very small compared to the blue. So from a numerical modeling perspective, it's very hard to do this because we tend to represent the ocean in a Z layer. I'll show you there's more, we're getting more advanced now, but imagine you have a Z layer just like the dashed line on the top, but then the mixing must happen kind of across that or perpendicular to that. It's very, very hard. And inevitably, you have spurious mixing. When you're discretizing an equation, you will have spurious mixing associated with your advection scheme and other operators. And that spurious mixing is much larger than what nature is expecting you to do. So any small error, it translates into a big error in the model. So this is very, very large. And as I mentioned before, because there's very little mixing, the water masses can be traced. And then there's a variety of water masses that have been named, like Antarctica bottom water, Antarctic intermediate water, North Atlantic deep water. And that's because of the small mixing that they experience once they sink towards the deep ocean. Okay, so the bottom line for climate studies is performing long climate scale simulations at eddy resolving or even eddy intermediate resolution is not practical. One must live with the deep ocean not being at equilibrium in most simulations. Spurious mixing in the interior, which I just talked about, can significantly degrade the solution. Then the heat capacity of the ocean is much larger than the atmosphere, and that's why the ocean is an important heat reservoir. And then finally, the ocean contains the memory of the climate system. And again, that's associated with this heat capacity as well, which has important implications for long-term prediction studies. So you can use the past state of the ocean to infer the future because of this memory. Okay, now let's move to the equations that we solve in the ocean models. And I'll be very superficial. We don't need to worry about the details. I'm happy to talk about details for those of you interested offline. So we have 7 equations and 7 unknowns. We have 3 velocity components, 1 equation for potential temperature, 1 for density, 1 for pressure, 1 for salinity. Plus, if you're dealing with ideal age, CFCs, there is 1 extra equation for each of those tracers. And these passive tracers, as we call, they follow the same equations as salinity. Okay, so 7 equations, 7 unknowns. And then before we solve the equations, we go through some basic approximations. So the first one is the so-called hydrostatic approximation, where when you have the water parcel, when you have inversion in density, so the densest water is on the top, and then you have lighter water below. So this is the water column becomes statically unstable. in nature, you have this overturning, these like so-called Kelvin-Helmholtz instabilities that developed. But we don't allow this to happen when we do the hydrostatic approximation, because all the vertical tendency is excluded in the momentum equation. So the only acceleration that we allow in the vertical is because of the gravity. So we don't allow like this overturning to happen. And instead, if we see that the water becomes unstable, we just apply very strong mixing and homogenize that. So that's one. The second one is the so-called Boussinesq approximation, where the changes in density compared to the mean density are very small. So we can define density rho as equal rho naught, so mean density plus rho prime, which is a perturbation, and rho prime is much smaller than rho naught. So we can say just rho equal rho naught. We do that everywhere but in the hydrostatic equation. And then the other one is the continuity in compressible form. So we cannot deform seawaters, so what flows into one side of a control volume must go out in one of the other sides of this control volume. Then the thin shell, and the best way to exemplify that is through a piece of paper. So this is the aspect ratio in the ocean. So the depth is much, much smaller than the horizontal, and even better with like a A4 or like a ladder type of piece of paper. So the depth is much smaller compared to the horizontal extent. And what that does is you can simplify, especially in the Coriolis force, you can retain only the zonal component, or the horizontal component, I should say. The vertical component of the Coriolis force can be neglected. And then spherical Earth, so the geopotential surface can be approximated by spheres. And then finally, turbulence closures. So what I said before, these processes that we cannot represent because of resolution, they must be parametrized. And that is, again, a lot of the business that we do, and it's a very hard problem most of the times. To represent a feature that's not present and not resolvable by your grid, using the information that the model contain. Okay, so horizontal momentum equation, and this is in Cartesian form. Vertical momentum or hydrostatic equation. And then we have mass conservation continuity equation, which, because of the Boussinesq approximation, can be simplified by just the divergence of velocity must be equals to 0. Then one equation for temperature. So this is advection diffusion, and then usually there's a source and sink term as well, which is not represented here. Similar for salinity. Then a nonlinear equation of state, which is very complicated, so I'm simplifying here. And then, as I said before, if you have a passive tracer, you would do just like you do for salinity or temperature. All right, now in terms of boundary conditions, you have fluxes exchange at the surface, so momentum tracers. At the bottom, with the new model, we allow for geothermal heating. So next to these major ocean ridges, in the middle of the ocean basins, you can have these thermal vents that are releasing heat. And with the new model, we can receive that heat. Is very small. It's like 0.1 watts per meter squared globally. But it can be important for biogeochemistry, for example. So with the exception of geothermal heating, there is no other source of tracer fluxes at the bottom. There's no normal velocity at the bottom is 0. And then we normally apply a quadratic bottom drag law. At the lateral boundaries, which the bottom is the lateral boundary. As you go, if you think of a bow, like bow shape, like the bottom becomes your lateral boundary. There is no tracer flux. The flow normal to the solid boundary is 0, and we apply the no-slip conditions for velocity. All right, in terms of horizontal grid staggering, I will talk about two options. So this is the one that was using the old model, POP. Is the so-called Arakawa big grid, where you have your tracer points. So this is a grid cell. And then in the middle, capital T, those where the tracer points live. And then your velocities U and V are on the corners of your tracer cell or your model cell. And this is the top view. And there's some advantages in using the Arakawa grid. So it naturally fits the no-slip boundary condition. You can get a better dispersion relation for Rossby waves at coarse resolution model compared to the C-grid. And then also smaller truncation errors in the Coriolis term. The disadvantages are that in order to represent a flow going through a channel, as in this schematic, so the green points are land and the bluish points are ocean. And in order to have the flow go from one side to the other, like through that channel, with the big grid, you need at least 2 grid points because the velocities reside on the corner. So that way, the only way you can have the flow go through. So it is challenging because, again, if you go low resolution, like 2 degree, some of these passages are much smaller than 2 degrees. So you have to make them much larger than they are in reality to represent the flow going through. And also, there's large fluctuations in the pressure gradient terms when you use the big grid. And again, this is what was used in POP2 model that you guys will still run, but no, it is the model used up to CSM2. The other grid is called the Arakawa C grid. And again, this is a top view. The tracers still live on the middle of the cell, capital T. Now the velocities are staggered. So the V velocity is on the top and bottom faces at the middle, and the U velocity is on the east and west face, again, at the middle. So they are staggered. And then the Q points on the corner, those are the vorticity points. Okay, so the advantage, first of all, it allows for a single point channel. You can have now a single point, and the flow will go through because you will have either the U or the V velocity being active. And then the disadvantages are the Coriolis acceleration requires some averaging because now U and V are in different points. So in order to compute Coriolis, you need to average them on a single point. And every time you do averaging, you introduce error. And then the other one is the dispersion relation for Rossby waves at coarse resolution. So we're talking about like 2-degree models. It is degraded compared to the big grid. And this is the staggered used in MOM6. Okay, another very important aspect, in addition to horizontal grid staggering, is the vertical coordinate system. So these are kind of the 3 most important coordinates that have been used. So the Z coordinate on the left, where you have constant geopotential, so those are fixed lines in the horizontal as a function of depth. And then the so-called terrain falling or sigma coordinates, which follow the topography, the one in the middle. And then finally, the isopycnals, the one on the right, that follows your density structure. The sigma coordinates are important for coastal models where you're interested in understanding, especially near the topography, how things behave. And each of them have its advantages and disadvantages. In an ideal world, we would combine all of them. And that is what these so-called hybrid vertical coordinate systems try to do. They try to combine all of these and keep the advantage of each of them in certain areas. And this is a very active area of research. We're still trying to find and come up with algorithms that can combine these coordinate systems in a good way. And all boils down to what I said earlier. We are trying to minimize the amount of spurious mixing in the ocean so that we can have very little mixing once the waters are synced. Okay, this is an example of the vertical grids using CSM. On the left, this is with MOM6. So top is a hybrid is a Z-star near the top. So you see very dense layers that are all geopotentially, so a function of depth near the top. And then they get spaced out, so they become isopycnal once you reach a certain depth. And it's complicated how that works. I'm happy to talk about afterwards for those of you interested. This is a default option in MOM6. You also have the option to switch to a Z-star coordinate, which is the one on the bottom. So Z-star is similar to the Z coordinate using POP, which again is constant throughout the horizontally, and then you change the function of that. But typically, we use this kind of hyperbolic tangent function to build this vertical coordinate. You want very high resolution near the top, where you have exchange with the atmosphere. You want to resolve smaller scale processes, and then it becomes delta Z becomes larger as you go towards the bottom. Okay, so in terms of options to run the ocean model in CSM, we can do fully coupled mode, what we call bCompSet, as you guys already have learned probably. And then you can do ocean only, what we call CCompSet, where there's not even a sea ice. And we rarely run ocean only CCompSet. More often, we run the so-called GCompSet, where you have an active ocean and an active sea ice. And when we have the C or G CompSet, we must specify the atmosphere, and that's the so-called coordinated ocean ice reference experiments, or CORE. It started with CORE, and now we can do like a repeated year, the interannual forcing, or you can just force with the same year repeatedly, the normal year forcing. So that's how we started doing these ocean-only processes. Then there's now a GRA 55, which is being actually retired, and there will be a new forcing protocol that's being developed at NCAR coming up next year. So if you run ocean-only, either G or C CompSet, you must specify if you use CORE, normal year, or interannual forcing, or GRA. And you can do the same thing with GRA, like repeated or throughout different years. All right, horizontal grids. We have two types of horizontal grids in CSM ocean component. You can have the so-called displaced pole, where the singularity point is moved to Greenland, as you can see here. And this is what was used in POP for the 1 degree workhorse. It is also what we used for the wave model in CSM3. That's the GX3 grid. So it's a nominal 3 degree that has the pole displaced to Greenland. And notice that we do equatorial refinement, so near the equator, we increase the resolution. So when we say 1 degree ocean model, it's nominal 1 degree. No, it actually varies the resolution throughout the globe. Not much as in an unstructured grid, but no, it does vary. And the other type of grid is the so-called tripole grid, which is what's used in CSM3 MOM6. In this case, notice you have the two singularity points in the northern hemisphere, and then usually we do one in Canada, the other one I think is in Russia, and depending on the grid. This is an example for the workhorse nominal 2/3 degree grid that we use. And again, we apply equatorial refinement up to 1/4 degree in the equator. All right, now let's dive into the MOM6 model. So the modular ocean model version 6 dynamical core is a finite volume solver. You can either use the hydrostatic Boussinesq, which I talked about, both hydrostatic approximation and the Boussinesq approximation. But in this model, you can say, I don't want the Boussinesq approximation. I want to run with non-Boussinesq. And one advantage of running with non-Boussinesq is for sea level rise studies, that in that case, the model contains the effect of the ocean acting on the sea ice. So that if the temperature increases, you see a response in the sea level, with you immediately, or like resolved by the model, contained within the model. One particular feature of MOM6 that's very appealing is the so-called arbitrary Lagrangian Eulerian framework, AO framework, which allows one to do the generalized vertical coordinate. So you can use any vertical coordinate that you wish, that you can even come up with your own, or a combination of them. In this example, you have Z coordinate, isopycnal, terrain falling, and you can even, again, combine all of them. And because what the model does is underneath, the equations that it's solving is just a bunch of stacked shallow water equations. So it's a bunch of layers, one on top of each other. And then you use the AO framework to remap. So you say, okay, I know how my layers are stacked, but I want you to represent now this into the Z coordinate that is on the top right. And then there is an algorithm that will go and remap between what the model is resolving and what the user wants. And because of that, there's no vertical CFL. So there's actually no vertical velocity in this model, which means like you can go very fine resolution in the vertical without having a constraint on your time step. We have subcycling of gravity waves, so time split between baroclinic and barotropic. And then we also have built-in wetting and drying, and I will show how that plays in one particular example. There is a whole soup of parameterizations available, or subgrid scale parameterizations available in MOM6 for mesoscale eddies, for surface boundary layer, for submesoscale eddies, shear mixing, shortwave penetration, bottom under layer, geothermal, internal tight-driven mixing. I'm not listing all of them. There's a lot of them. This is an open development model. Anyone can go on GitHub and contribute to the development. You are welcome to do so. And because of that, the input from the community, it grows very, very fast. Like there's always, the new capability that someone comes up with, it will be likely come into MOM6 in a timely manner. All right, overflows in CSM MOM6. Because of this option to choose your vertical coordinator and play with it, you can explicitly resolve overflows. So overflows, they play a critical role in the climate system because they form the bottom intermediate waters and that supply the water masses to the deep ocean, which drives the global meridional overturning circulation. So this is an example of the Nordics overflow. You have the Denmark Strait on the top left, and then the Ferrobeck Channel overflow on the bottom right. They go from the Nordic seas into the North Atlantic, and those are like just dense waters going down the slope. And in POP, for example, you had to parameterize this process because it uses Z vertical coordinate. But in MOM6, and this is a couple run a simulation that I showed yesterday to the development CSM development meeting. You can explicitly see. So this is the Denmark Strait overflow. You can see how the vertical coordinate allows you to represent this dense water going down the slope, and that's because we become density is a function of the density as you go below the surface. So Z star near the top, as I said before, but near the bottom where the plume is going down slope and in training is density. So it allows you to represent that explicitly. All right. In addition of doing global simulations with MOM6, in CSM, you also have the option to do the simplified configurations like the CSM Aqua on the left or Ridge on the right. So these were work done by a grad student a few years ago, Xiaoning Zhu, and she kind of lead the way. And there were many other studies that have been done with the simplified configurations in CSM with MOM6. So it is a new capability coming with the new model. Another one, and that is a good example of this built-in wet and dry, is you have the option to represent ice shelf cavities. So here you have an ice shelf cavity, that's the bedrock, and then the ocean is on the right. It's initially homogeneous, so it's an idealized simulation. And then I will animate this, so then the warm water at the bottom is melting the ice, and then it melts the ice, then you have this buoyant plume that's very cold and fresh, 2 minutes, thank you, that then raised to the surface of the ocean. And notice how the initial shape of that shelf I kept just to give you an idea of you're changing where you used to be land, now it's becoming ocean. So that's a good example of the wetting and drying capability in MOM. All right, you can also do regional modeling. Here's an example from the Caribbean Ocean that was led by Giovanni Sejo. So this is, again, within CSM. And this opens up the capability for a lot of science, for example, for studying coral reef restoration, fisheries, marine protected areas. So you can define your regional domain, use open boundary conditions, and go much higher resolution than you would go with the global model. If you're interested in regional modeling with CSM MOM6, there's a tutorial coming up. You can scan the QR code, or you can come talk to one of us. We can point you to it, but I think will be end of September. And then finally, some helpful resources. I won't go through all of them, but there's webinars, there's diagnostic packages, there's regional tools, and then the CSM forum as well. And then finally, thank you for your time. Happy to take any questions. Please subscribe to the Ocean Model Working Group if you want to get involved. No questions? Do we have time for questions?
Yeah, until 9:15.
Okay. I was wondering, is it more about the horizontal and vertical grid structures that led to the top 2 to MOM switch?
The choice of vertical coordinate in MOM, it was definitely one of the appealing for going to MOM. But the main reason is there was the development of the POP model was ended. So POP was developed between NCAR and Los Alamos National Lab. And then Los Alamos took a different direction a few years ago, and they started building a new model. And then that's when we had to choose to go in a different direction, and that's how MOM6 came in.
Follow-up. How often do you guys joke about choosing mom over pop in the divorce? Because that's all I would do.
We never talked about divorce. Yeah.
I'm curious, are tides modeled in MOM6, or does that depend on what kind of forcing we're using?
Yeah, if you do regional modeling, you can provide the tides at the boundary. That's usually what people do, depending on the size of your domain. In the global model, you can specify tides as a gravitational, gravity potential is not known to the boundary because there's no boundary. So there's a way to specify tides. And William Shu, is William here? Yeah, William is the new ocean model science liaison for CSM, and he is the person to talk to you about tides, especially in the global model. That will be one of the things William will implement in our simulations.
Tides behave differently depending on whether we're using a Business versus a non-Business model?
No,
Okay.
not that I know of. Yes.
Why the resolution is enhanced in the tropic if the eddies produce mostly in the extratropic?
Good question. In the tropics, in the equatorial tropics, we have these tropical instability waves, Chiwi waves. Now, they're not eddies, they're waves. I let you go and investigate what's the difference between eddy and waves. But no, the Chiwi waves are important for many things, including ENSO exchange of properties between the ocean and the atmosphere. So we want to represent these waves. That's why.
I'm curious about when you show the resolution, it's also related to resolution as well. So when you show the resolution in South Africa, I was wondering how having a higher resolution influences the variability, let's say of sea surface temperature variability, if it increases the white noise, for example, or how lower resolution sea surface temperature versus high resolution sea surface temperature compares in terms of low frequency variability, let's say in the equatorial Pacific Ocean.
Yeah, I don't know the answer to all of this. There is, you're right. Like you go high resolution, you tend to have more variability just because of the resolving more features. In terms of, it can be for good or bad reasons. Not necessarily can be a better model because you have that higher variability. But that is something that can be a science question that you can look at and say, what is the difference between this low and high resolution model for SST, for example, and which one is more realistic and where, and
I was curious because, for example, with CSM, I have noticed, for example, El Niño events are more frequent from observations. And I was wondering if we increase resolution, if that will even increase the frequency of having ENSO events compared to observations. But
yeah, ENSO is complicated because it's not ocean-only phenomenon. So there is feedback. But if you're interested, I can point you to this. So there's now the Mesoclip data set, which is a high-resolution CSM model, which not necessarily has a better ENSO representation than its equivalent low resolution. So it becomes interesting when it's a couple phenomenon, and then you play with resolution. So not necessarily you're going to get better as you go high resolution. Yes.
I think in previous CSM1 and CSM2, the Greenland ice sheet was stationary, and I think somebody mentioned it isn't in CSM3. Would Greenland ice sheet melt in the coupled simulations, would that interact with the ocean model?
Yeah, it's a one-way interaction. So the ice sheet can melt from the top and also basal melt within land. And then there is a runoff. It can be liquid or frozen that gets released into the ocean. So it's a one-way. So what the schematic animation that I showed of the ice shelf, which applies to Antarctica, you don't have ice shelves in Greenland, it is future versions, hopefully, that will have that two-way capability.
For the wetting and the drying, the example you showed was exchanging, I guess, a boundary with ice, which is already in the ocean.
Yeah.
Can you do exchanging of boundaries with land, wetting and drying onto land?
Yeah, in principle you can. It's the same idea. So the ice example, no, the ocean was present there. It was just infinitesimally small, like it was angstrom, like 10 to the minus 12 meters. And then once the ice melted, it inflated. So in principle, you can do the same thing, picture like a domain where everywhere is ocean, but then you say, here is very thin ocean, and that's will be land. But in practice, it's very hard because it requires the coupler to know that. So usually when we come up with a global domain, we say, we have the mesh files, and we say, here's my land sea mask, and that gets fixed throughout the simulation. So we would require within CSM to restructure the mediator, the coupler, and say, okay, you will decide what is land, what is ocean every now and then or something.
And also the land model has to be set up.
Exactly, yeah. So from the ocean model side, we can do that. But then from the couple side, it requires a lot of work. I'll be here for the next lecture too. I'm happy to take more questions later if you guys have to. Thank you.
Thank you, Gustavo. All right. Great. Then I think, yeah, you'll stick around if other people want to discuss during the break. Now we're going to have a break until 9:30 and then come back for another ocean lecture. Everybody's got their coffee ready to go. All right, we'll get started on our next lecture. Peter Gent is a senior scientist in the oceanography section, and he'll be talking about parameterizations in physics.
So it's very appropriate for me to take over from Gustavo. Remember, Brazil are out of the World Cup. England are still in the World Cup. So there we go. Now, there are three things that Gustavo mentioned which are worth repeating. First, the ocean component is the most important component in the climate model. It has virtually all the heat. It advects that around the world and gives it back. And it has the memory in the climate system. So if you want to make forecasts of things like ENSO using a climate model or seasonal to interannual predictions, it's the key component that has the memory that makes those predictions possible. Secondly, it has two big differences from the atmosphere. The atmosphere has things going on at the surface and is therefore heated from below. Things like convection bubble up from the surface. So things occur in the atmosphere and the surface and go up. In the ocean, it's completely the opposite. All the forcing is at the surface of the ocean. Wind stress, heat flux, freshwater flux, anything else like CO2 gets put in at the surface and then goes down and somehow gets into the deep ocean. So the vertical mixing scheme is probably the most important parameterization in the ocean component. But the other thing Gustavo mentioned is that the Rossby radius of deformation is a lot smaller in the ocean than the atmosphere. And the reason is, as you go up in the atmosphere to the very high levels, the density is almost zero. So you get an order one change in the density of the air between the surface and the very high altitude. In the ocean, it's completely different. It's all water, and so the density changes are like a fraction of 1% between the deep ocean and the surface. Even in the equator regions, where it's very warm, that difference is very small. And that Rossby radius of deformation, which is the scale where baroclinic eddies form and get created, is therefore very much smaller in the ocean than in the atmosphere. In the atmosphere, it's like 1,500 kilometers. Its baroclinic instability produces the highs and lows that we all know. In the ocean, the Rossby radius of deformation is probably just over 200 kilometers at the equator. But as you go further poleward and the surface gets colder and colder and colder, the density difference decreases. And so the Rossby radius of deformation decreases. So as you get towards the very high latitudes, the Rossby radius is probably on the order of like 10 or 20 kilometers. Therefore, an ocean model that has a 1 degree or down to say a ½ degree resolution cannot resolve these mesoscale eddies. And therefore, their effects on the mean flow need to be parameterized. This is the second most important. Sometimes I think of it as the first most important. But those are the two parameterizations I'm going to talk about: vertical mixing and mesoscale eddies. So the vertical mixing scheme that's used in the ocean is called the K-profile parameterization, KPP. It was first proposed by Large, McWilliams, and Doney in 1994. And what it says is unresolved turbulent vertical mixing due to small-scale overturning motions is parameterized as vertical diffusion. So here, we are guided by studies of observations and in the atmospheric boundary layer, and we have the time rate of change is equal to the advective part in the vertical equation. So the correlations, say, between temperature and vertical velocity averaged. And that average is parameterized as minus a coefficient, kappa, either diffusivity or viscosity, times the vertical gradient of the quantity itself. So you plug that into here, and you get dx dt is d by dz kappa d by dz of x. So it's like vertical diffusion. But one of the key inventions new was in the KPP scheme was that the vertical diffusion also had a counter gradient term in the scalar equations for either temperature or salinity. So it had this gamma x term over here, which, as I just said, was new, and the KPP people thought that was very important because it then produces quite large diffusivities below the boundary layer, which mixes temperature and salinity quite deep in times of very strong surface wind stress, such as strong forcing from mid-latitude atmospheric storms. So KPP involves 3 steps. First, you need to determine the depth of the boundary layer, D. Then you calculate the diffusivities in the interior of the ocean. So this is below the boundary layer, where the surface forcing is not felt very much. So this is in the quiescent parts of the ocean. And then, having determined those two, you can evaluate the diffusivities in the boundary layer itself. And that diffusivity depends on the surface forcing. In terms of momentum, that's the wind stress, the boundary layer depth, and the interior diffusivity. So that's why you need to calculate these two first before you do number 3. So, how do we calculate the boundary layer depth? So we go down in the ocean at the first of the levels below the surface, and we calculate a bulk Richardson number for each level. And a bulk Richardson number is the difference between a reference buoyancy near the surface and the buoyancy at depth d times d divided by the square of the velocity difference between a near-surface reference horizontal velocity and the velocity at depth d. And we add a little term there called unresolved shear, which is a bit of a fudge just to make sure that the Richardson number doesn't go to infinity if these two happen to be equal. Now, the Richardson number measures the stability of stratified shear flow. There's a very famous theorem about the Richardson number getting below a quarter to produce Kelvin-Helmholtz instability. So it measures the stability of the stratified shear flow, and with this calculation of the depth, so you go down each level in the ocean until you get to a depth where this bulk Richardson number gets below 0.3. And when we do this, this Richardson number measures the stability of the shear flow, and from the paper it says boundary layer eddies with mean velocity Vr at the surface and buoyancy Br at the surface should be able to penetrate to the boundary layer depth d, where they first become stable relative to the local buoyancy and velocity. So that's how you calculate the boundary layer depth. Once you go below that, this is the calculation of the interior diffusivity. So this is where the ocean is quiescent, below where the mixing is happening. And there are a number of contributors to this interior diffusivity, which is much smaller than what's going on in the boundary layer. There's one called unresolved shear instability. There's one due to internal waves. Internal waves can propagate around in the ocean, and they break in certain places, and that produces vertical mixing and turbulence. There's a phenomenon in the ocean called double diffusion, which is too complicated for me to explain now, but it happens because the diffusivity rates of salt and heat in the ocean are quite different. So you can get different diffusive properties, and you can get what's called double diffusion overturning. You can also, this is where tides come in the mixing. The tides break over steep topography in the ocean, over the mid-Atlantic ridges and the ridges and over steep topography. So this is where tides come in, and there's a parameterization globally for that. And then there's this local static instability, as Gustavo explained nicely. If you get a place in the ocean where the density is unstable, so it's denser above a place where it's less dense, this will get mixed out by vertical mixing. But because we have the hydrostatic approximation, that won't work. So we get rid of that by putting a very large diffusivity in the vertical to smear that out. So that can be large. All the other values are pretty small. So how does this work? So this is a plot from their 94 paper. And on the top here, we've got some observations of temperature down to 150 meters from Ocean Weather Station Papa, which is located at 50 north, 145 west. So it's in the North Atlantic off Vancouver Island. See, these are the observations, and this is what KPP simulates. So you can see that the boundary layer depth is quite deep, close to 80 or 90 meters during the first part of spring. And then it shallows. And this is because as spring and summer kick in, you get sunlight heating the surface of the ocean, which creates a more buoyant surface. And also, the winds are weaker in the spring and summer than in the winter. So the boundary layer depth shallows all the way through July, where it comes to about 30 meters. And after that, as you go longer into the fall and then the winter, the boundary layer deepens because A, you've lost the solar heating because it's going south of the equator, and you have more vigorous mid-latitude storms. So most of this mixing is caused by turbulence created by mid-latitude storms mixing it down. So by the time you get to November, the boundary layer depth is at its deepest, and it's about 100 meters. So boundary layers, these are typical of mid-latitude boundary layers. They vary from like 30 meters to 100. They have a seasonal cycle, which repeats, and the same in the Southern Ocean, except you'd be 6 months different. You can get shallower mixed layers right at the equator for different reasons. Anyway, this is what the KPP produced, and I'll leave it to you to judge how good it is. But the authors of the paper thought it was great. They thought this was better than anything that had been produced by a previous vertical mixing simulation. And KPP has now been used not only in all the CSM models, but in many, many ocean models around the world. In fact, it has a citation count well over 3,000. Every ocean model, even if you go to eddy resolving, 1/10 of a degree or finer, you might get rid of an eddy parameterization, but you don't need, I mean, you absolutely do need a vertical mixing scheme. So a vertical mixing scheme gets used in every ocean model and every simulation. Now, that's enough about that. We now come on to my favorite parameterization. This is about what to do about mesoscale eddies. So Jim McWilliams and I first proposed this in 1990. And 20 years later, I was asked to write a review, which got published in Ocean Modeling in 2011, called 2020 Hindsight. So if you want to read some more, don't read that. Go and read this. I thought I understood that. I do understand what was going on here. So go and read that. So I don't think I need to do that very much, but if you go to eddy resolving resolution, you get a lot of variability. These are, in fact, the TWE waves, the tropical instability waves at the equator. And now I'm going to show the same plot that Gustavo showed about what goes on off the tip of South Africa in a 1/10 of a degree and a 1 degree model, just showing that there's a huge amount of more variability in the 1/10 of a degree. When we run 1/10 of a degree models, we call them eddy resolving, so you don't need an eddy parameterization. For either 1 degree down to at least a 1/2 degree, or coarser, you definitely need a parameterization to simulate what the eddies do. So when I first got into ocean modeling, the parameterized effects of eddies were parameterized by Laplacian horizontal diffusion in a z-level model, because that was dead easy to implement. The models are z-level, so you just implement diffusion. But ocean observations tell us that the mixing along isopycnals is around 10 to the 4. Mixing across isopycnals is about 10 to the -3. So you've got a 7 order of magnitude difference between the along isopycnal and the cross isopycnal mixing. And as Gustavo nicely pointed out, that very, very weak cross isopycnal mixing is why oceanographers originally named the ocean water masses. For instance, water comes out of the Mediterranean, which has a lot of evaporation, extremely dense, comes through the Strait of Gibraltar. It's called Mediterranean seawater, and you can follow that all the way across the Atlantic as it slowly sinks, because its temperature and salinity properties that get set when it comes over the sill at Gibraltar maintain across the Atlantic, and you can tell that it's from the Mediterranean rather than from elsewhere in the Atlantic. And that's because cross isopycnal mixing is very, very small. So the trouble was with having this along depth was that if you put in 10 cubed, then you would make like a sine of that small angle, which are small. The slope's around 10 to the -3, but you would still have 10 to the 7 times 10 to the -3. You would still have far too much cross isopycnal mixing. So it was resolved that in z-coordinate models, you needed to change such that the isopycnal mixing was along the isopycnal. The isopycnals are the surfaces of constant density. So that's represented here. That was implemented in the mid-80s in the GFDL model first. But what we proposed in 1990 was that the effect of eddies wasn't just a diffusion, but it was also an advection. So we proposed an extra eddy-induced advection, U star, which is three-dimensionally non-divergent, just like the mean flow. And we proposed that it was like dependent on kappa, which we thought was the same kappa as the diffusion along isopycnals, times the gradient of rho divided by rho c, which is the slope of the isopycnals. So as the isopycnal slopes increase, this velocity increases and tries to reduce the potential energy and flatten the isopycnals. And that simulates what baroclinic instability does. As the isopycnal slopes increase, you get baroclinic instability, produce eddies, and they try to reduce the potential energy and flatten the isopycnals. Now, where does this have the greatest effect? And the answer is in the Southern Ocean, where there is a strongest current in the world ocean called the Antarctic Circumpolar Current. And just like its name implies, it's unique in the ocean because it's circumpolar. All the other currents are like the Gulf Stream, Kuroshio, etc., are in basins which are partially bounded. Yeah, the ACC goes all the way around, goes through Drake Passage is its narrowest place, and it's driven by a very strong southern hemisphere jet in the atmosphere. So this is Antarctica. So, this is, as I said, all these water masses are named: Antarctic bottom water, North Atlantic deep water. And so this southern hemisphere jet is coming out of the board towards you. And we're in the southern hemisphere, so the Coriolis force is producing things going to the left. So it produces a surface current which has a Coriolis component which is going to the left. Now, that Coriolis component is strongest where the center of the southern hemisphere jet is, and the current is produced is the strongest. So you go to the fringes of the jet, you've still got a little Coriolis going to the left, but it's weaker. So you have convergence there, stronger and weaker. So you have convergence of water there, and where does it have to go? It has to go down. On the southern side of the jet, the opposite is true. You have a weaker Coriolis northward flow there and a stronger one there. So you're producing a region of divergence there. And to fill that divergence, the water has to come up from below. So the mean flow is producing a clockwise flow of sinking here and coming back up here. That clockwise flow tends to steepen the slopes of the isopycnals in the Southern Ocean here. These are isopycnals. So in reality, that produces baroclinic instability, produces eddies in the Antarctic Circumpolar Current, and they remove potential energy and make the isopycnals flatter. The GM parameterization does that by producing a counterclockwise flow doing this, which counters the clockwise flow of the eddies. So the mean flow is producing a clockwise circulation doing this, and the eddies produce an I'm in America, so a counterclockwise flow, balancing the mean flow. So when we first proposed this, we took a version of MOM, it's actually MOM 1, and put in KPP and the GM parameterization plus, when we add GM, we had the mixing along isopycnals. But the first run we did, and we ran it for 10,000 years out to equilibrium, produced this of the Meridional overturning circulation. So you've got the UdX to VDY plus dWdz is 0. So if you integrate in x, you produce an overturning circulation, a stream function, which is telling you where water's going, north and south or up and down. So what this is showing here is that water's going clockwise around the positive contours here. So it's sinking in the north, and that sinking is almost all in the North Atlantic. So this up here is the AMOC. Everybody should have heard of AMOC by now. Every day you wake up, turn your computer on, it's telling you either there's going to be a monster El Nino, which is terrible, or that the AMOC is going to collapse. This is the AMOC. But in the southern hemisphere, here you've got this cell forced exactly in the way I just described, near the ACC. And to its south, you've got rather a strong circulation there producing Antarctic bottom water, which is stronger than we know it is. Then we ran this second one, including GM, again out to equilibrium. And this is the overturning circulation you get just from the mean flow. So it's a little different than that, but not too different. In fact, it's increased the AMOC from 12 to 14. You've still got this positive cell here, but you've got a much weaker Antarctic bottom water. But if you produce the overturning circulation from the sum of the mean flow and the eddy-induced flow, you get this. Hasn't changed the AMOC very much, but look what it's done in the southern hemisphere. It's almost exactly balanced out the overturning by the mean flow. So it's done exactly what we wanted to do. It counteracts the mean flow overturning, and it produces a much better simulation. Because this one, think about what this is doing at the surface. At the surface there, it's taking water towards the equator, to the right. So it's taking very cold water and pushing it above lighter water. So there, then you're statically unstable. The colder water is denser than the warmer water. That effect is completely gone away in this simulation. So it has a really strong effect on where that, when you get unstable in the column, that strong vertical mixing kicks in to get rid of it. That strong vertical mixing occurs in very many places when you've just got horizontal diffusion. But in the GM, it vastly reduced to places like the Nordic Seas, Labrador Sea, the Weddell Sea, and the Ross Sea, which are, in fact, exactly the places where we know that deep water is formed. This was a complete surprise to me, but it was very important when we thought how important it would be in a climate model. And if you went to a real oceanographer, say at Woods Hole or Scripps, who goes to sea and whatever, and asked them, where are the deep water locations, they would say this one is far, far more realistic than this. Now, GM summary. Have I still got a few minutes here? So it mimics the effect of unresolved mesoscale eddies as a sum of diffusive mixing along isopycnals and advection of tracer by the eddy-induced velocity. That extra advection is adiabatic and therefore is appropriate for the deeper ocean, below all the boundary layer, below where all the mixing is occurred in the deep ocean. And it acts to flatten the isopycnals, thereby reducing potential energy. So it's the equivalent of what baroclinic instability does. And what we found was it eliminates any need for horizontal diffusion in z-coordinate ocean models. And now, as far as I know, ocean model of non-eddy resolving resolution will use horizontal mixing. As you go down to like a 1/10 of a degree or finer, then they go back to horizontal mixing. But anything of a 1 degree or that sort of resolution does not ever use horizontal mixing anymore. Now, implementing of this into an ocean model, I should have been more diligent in pointing out that these results were in what we called the NCAR CSM ocean model. Started with MOM, was in the NCAR CSM ocean model called NCOM. You need to remember NCOM. So we put this in to the first version of CSM1. And lo and behold, with some developments in the atmospheric component as well, the result from a 300-year run of CSM1 was that we got a stable surface temperature distribution. This is all surfaces, land only, ocean sea ice. And this was the first ever run which retained a stable surface temperature distribution without the use of flux corrections or adjustments. You may be too young to know what flux adjustments were, but they were arbitrary adjustments to the heat and fresh water that were determined because if you didn't have them and you started an integration from modern day climate, it would drift away. So what you did is you ran your ocean model and decided what heat and freshwater fluxes it wants. You ran your atmosphere model and did the same. You differenced the two, and that was your flux adjustment. And then you implemented those every time step in the model. So it was a complete fudge because the ocean and the atmosphere components weren't consistent enough with each other. CSM1, the first version, run in the late 1990s, was the first one ever to do that. And these components in the ocean, KPP and the GM, were really important in producing this result, which was a big, big result at the time. Other groups around the world basically didn't believe us for a while. And the GFDL director wrote to our sponsor at NSF a letter telling him that we must have cheated to get this result. But we hadn't. Now, I've just got time to show some poetry. You weren't expecting poetry, were you? But in 2000, there was a meeting in Limerick in Ireland, and I was asked to give a talk on GM. Well, the temptation was too much. I had to come up with a limerick. So all the best limericks start like this. There once was an ocean model called MOM. That's how they all start. But how do they finish? There once was an ocean model called MOM, which occasionally used to bomb. But eddy advection and much less convection turned it into a stable NCOM. Thank you. Any questions? Yes.
So I noticed that in the figures from the 94, I think it was, paper, there's no real resolution of the Bering Strait as a waterway. How much did being able to actually resolve that opening of that waterway improve the physicality?
So if you wanted to look at the Arctic, it would be vital to do that. What it did in the Southern Ocean, it doesn't affect it very much. And we did that because A, the resolution was 3 degrees by 4 degrees. And in fact, in those old days, the fewer islands you had, or the more islands you had, the harder it was to implement one of the things that was in MOM that took most of the time. So we always used to try to have as few islands as possible. And as was talked about by Gustavo, the discretization said you needed 2 grid points to get anything go through the Bering Strait. So the Bering Strait would have been 6 degrees, which even I know is wrong. So the Arctic wasn't so good there, but we also, in that first CSM model, didn't have a really very good sea ice model as well. So the sea ice distributions were not so good, but it was that key. I mean, the big result from CSM1 was we got something stable without the use of flux adjustments. And what happened then was that, for instance, in the Australian climate model, KPP and GM got implemented in their model, and the flux adjustments that they needed to keep their model stable in the Southern Ocean, just where I said all the big effects were reduced from 250 watts per square meter, which is huge, down to 25. So it had a huge, big effect there. The next group to produce a run that didn't need flux adjustments was the Hadley Centre at British Met Office. And they put in GM. They still use, in fact, their own vertical mixing model. But implementation of GM and KPP in climate models around the world meant that within several years, that Hadley Centre was like in early 2000s, that more and more models could run without flux corrections. And now, no model runs with flux corrections unless you're producing a forecast of ENSO, where ENSO, to produce a realistic forecast, you need a realistic initial condition. And to get a more realistic initial condition, people put in small flux corrections just in the tropical Pacific. So really, the only justification for using flux adjustments is short-term prediction. Anything for longer climate these days, flux adjustments should not be used. And I've written a paper once saying that the use of flux adjustments changes the stability properties of the AMOC, the North Atlantic overturning circulation, Meridional overturning circulation, drastically. So when we're looking at, it's a hot topic at this point, what's the stability of AMOC? When you do that, you should never, never use a model with flux adjustments.
Yeah, sorry if I missed this, but in the calculation of the boundary layer and the internal, diffusivity or diffusion, one of the two, you have the unresolved shear term, and I could imagine that, you have the boundary layer where that fraction is equal to 0.3, and you're adding a squared term that you define as just unresolved. So I was curious, when you actually run your numbers, is that unresolved term some probability density function? Is it fitted to observe data? Because I would imagine that would alter the results of your fraction in a non-negligible way.
It's modeled on observed values, and it's small. Mostly that difference in velocity squared that's below is much larger, and it's a squared quantity. And as I said before, it was really that we were worried that that first velocity might go to 0 and the Richardson number would, and the model would stop. And you know, those quantities are squared. So you know, if you get a velocity difference in the resolved that's 2 or 3 times that other velocity, then its influence is 4 to 9 times as much. So it's a small term there. Yeah, all those ones which I didn't spend very much time on, how you set it in the deep ocean, are all based on distributions from observations. For instance, on tidal mixing, they determine where the tides interact with the topography, mid-Atlantic ridges, and so that's a spatial distribution. Same with internal waves. So they're all at least a spatial distribution, and then some of them, like the tides, are a function of depth as well. So yeah, so they're all based on observations as best we know them.
I'm curious about the hydrostatic approximation. So I don't study the ocean, but I study the atmosphere, and like, okay, if I'm interpreting what you said correctly, you were saying that because of the hydrostatic approximation, buoyancy instabilities wouldn't mix out, but in the atmosphere, I would expect that the hydrostatic approximation would resolve the instabilities.
Yeah, so very few atmospheric models use the hydrostatic approximation. So they resolve, because you're forced from below and things are turbulent up, they resolve their vertical, so their third component of the momentum equation, the W equation, is the full equation. Whereas in ours, we neglect dW, dt, and the advection of W, and just have a vertical pressure gradient balancing the density on the right-hand side. So it's that neglect of the vertical velocity equation, which says that you can't, if you're something that's unstable, you can't actually resolve that by vertical velocities. So we just smooth that out with a very large diffusion coefficient. In the atmosphere, that W equation is, you know, for when you're getting convection from force at the surface, is absolutely crucial. So you can't make that approximation. All right.
I have a question about resolution dependence. So when model resolution becomes higher, I think some of the eddy and mixing are partly resolved. Right. So in that case, I think the effect of eddy could be double counting due to the parameterization. So how should we adjust or tune parameterization depending on the resolution? Yeah.
So Gustavo showed that plot from Bob Holberg, that how well you resolve, because in the equator, if it's, you know, 200, if the Rossby radius is 200, 250 meters, a 1 degree ocean is partially resolving it. And as your resolution goes up, you partially or better resolve things further and further away. So Bob Holberg and GFDL there, then they have very weak GM in the equator and in the starts, you know, the subtropics, and then it starts to kick in where you're not resolving the eddies, and so you need the eddy parameterization to kick in. And as I mentioned before, when people run global 1/10th degree models, basically GM is most frequently not used, because they quote, resolve the eddies.
Okay, maybe Peter can stay a little bit for the break if we want to continue discussions. Great, let's thank Peter one more time. And now we're going to have another break until 10:30 and then come back in here for an intro to the lab. back. Oh, yeah. Sure. Okay. All right. You all know Cecile. She's been around, she's given the lecture, and now she'll introduce the lab.
Then today, I'm going to bring you in the next step of CSM. We are going to learn how to customize, debug, and modifying CSM. And basically, this is the 3 skills that every CSM user needs. Then it's how to customize a simulation, and we will do this through Namelist modification. To diagnose a failed run, it's troubleshooting model error, and then to modify the code, it's when you modify CSM. Then this is what we are going to do today. And on the website, it will be divided. I separate this in 3 sections. I never know how this thing works.
If you click it a couple times, it will wake up when it vibrates.
Okay. Okay, then. Yeah. Okay, then you can see. Okay, I will do this way. Then this is separated in 3 sections, and there will be exercise in the 3 sections. Then what I want to tell you that it's a quote of the Matrix. I can only show you the door. And basically, I can talk about CSM for hours and hours. I'm really good at talking. Then, but the real learning, it's when you are going to, what does this thing go? The real learning, it's when you are running the model yourself, and you are going to learn by running experiment, asking questions, making mistakes. It's when you learn the most. When everything works, you don't learn anything. And I will recommend it. I know a lot of us are really good at copy-paste. I'm a Nobel Prize in copy-paste. The notebook allows you to do copy-paste, but I recommend that you type with your little finger, you train them, and then you will do mistake when you do this. When you copy-paste, we test it, and in theory, it should work. But then I recommend you do copy. You don't do copy-paste, then you try to type. Or if you do copy-paste, really understand the command that you are doing. Then the first thing, it's how you are going to customize a namelist modification. And here you are running CSM. We saw that CSM, by default, it does monthly output. And let's say you want to look at daily cycle, not that useful. Then how are you going to change this? Or you want to do extra history file, or you don't like this spectral element grid in CAM and you want to interpolate, then this is the kind of thing that you can do in Namelist. Then it's hard to cover in a few minutes Namelist, but on the website, it shows exactly how to modify the Namelist. I have done again here like the schematic of CSM. You have the CSM code, you have the case directory, and it's where you are going to change the Namelist in user NL file. And it's explained on the website how to do this. And then the Namelist magically will appear into CaseDoc and into your run directory. There will be exercise about Namelist. The second thing that we are going to do, it's how to troubleshoot runtime error. And every day, everything works, but today, I get like something like this. This is the story of my life, basically. Truly. It's not exactly this way, but this is kind of. Then you have this error. What do? Then you will learn here to look at runtime error instead of guessing or crying. I cry a lot. But this is how you do this. And usually you are going to look at the log file. Then in the section troubleshooting runtime error, you will have log file here that you will, you have to read the documentation, but it's really in the log file that you will find information why your run crashed. And we are going to do something really fun. We are going to make the model crash in purpose, and then we will try to find out why it crashed. Then the exercise here, you can do copy-paste, and then it will crash, I guarantee. But it's, okay, then the last thing, it's source modification. Let's say CSM does almost everything I want, but not everything. Then maybe you want to output a variable that doesn't exist by default in CSM, or you want to change a parameter. or you have like a scientific ID and you want to test this, a new parameterization. How do you do this? Namelists are not enough to do this, and you need to modify the source code. Then I want to do a warning. Oh, not warming, warning. And it's really, my gosh, I just had this quickly this morning. Then yeah. Then this is not the choice, but warming. Yeah. This is the choice between the red pill and the blue pill, and again, it's coming from the matrix, and you have a situation that's really applied to what we do. The blue pill is when you don't modify CSM and you run as is, and the red pill, it's when you start modify CSM. And if you escape, there is no going back, I can tell you. But it's fun, it's fun. Then for instance, one of the example I tell you to do here, in the exercise, you will add a new variable in CSM. CSM will put temperature at some level, but let's say you want at a level that doesn't exist, and you will learn how to do this. And it's in the source modification. Then this is the goal by the end of the day, and I want to keep this short because, as I say, I can only show you the door. You are the one to learn. Then I have been in the lab. I have a few questions. Then people say, I have not finished Monday exercise. What should I do? Should I jump there? I want to say again, everybody come with different skill. This is not a race. If you haven't do Monday exercise, I recommend that you learn this before jumping after. You move, the tutorial is designed that you can move at your own pace. The second thing, I have completed everything already. Then you can help others. You learn a lot by helping other people. And the last thing, people get frustrated. Everything is called like 1850 basic. You have like, the case directory is called FT basic, the run directory also, the archive directory. Then if you go on this page here, it brings you where, yeah, on this slide, and then it shows you where to find the directory. You do cd, the change directory command. And this is basically what you have. And if you have any question, small question, we can talk. I have an activity for you, then don't go anywhere, but otherwise I will let you go in the lab. No question? Then don't go anywhere yet. Then, I don't know who have been watching soccer, but the Norwegian, they've been soccer fan, and they have like this huge, the whole group is doing like the Viking row, and they are all, I have an example here. It goes, yeah, this is for you. Then there is like somebody who, he will do pam, 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 row, pam, pam, row. And I was thinking that maybe we can do better than soccer fan, and it will be called the CSM row instead of the Viking row. Then, go sit. Then, do you want to? Okay, then I'm going, I ask them to film then, because I'm going to, yeah. Then if you understand the concept, I'm going to do, why you, the Spain, okay. Then, yeah, well, you look at Gustavo then. If I do, Gustavo, you know how to do the Viking row. Then it's ready, you are all ready. And I'm going to do, and you can film already, but they are going to do, yeah, okay, perfect. Okay, then ready for the Viking row. Then we are going to do, whoa. Row, 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 row. Well, I think we are much better than soccer fans. Okay. Okay, let's do. We are going, after I let go. Okay, let's go. We're going to start slowly, and we're going to increase the speed. Ready? Row, 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 row. Well. Okay. Thank you. No, we are better than.
You bring our trauma again. We just lost for Norway this Sunday.
Oh, sorry.
Oh no.
Oh, I thought we were meeting the experts. Oh my God.
Okay, lovely. Oh, cute. All right. Okay, awesome. Great. We're back. Lunch. Raya, the dog. So, we have our next exciting activity, which is the next ocean lecture. Keith Lindsay is a senior scientist in the oceanography section, and he'll be talking about biogeochemical modeling.
Can you hear me? Okay, good. Okay, great. That's a tough act to follow. A sweet, adorable dog. I don't think I'm going to be getting nearly as many oohs and ahs as the puppy got, but that's okay. So, as Sophia said, I'm going to be giving you information about ocean biogeochemical modeling. So the basic outline of what I'm going to talk to you about are large-scale ocean biogeochemical features, and this is just background about what are the features of ocean biogeochemistry that we try to capture in our model, and through processes that lead to those features. So I'm going to start off with what do we see in the ocean when we go and measure biogeochemical constituents in the ocean? What are the major features? And then I'll get into the processes that lead to those features. And I'm going to do a bit of a deeper dive on the modeling of one of those processes, that's biological productivity. That's just one of many processes that we have in our ocean biogeochemistry models. I'm going to talk a bit about how we assess the skill of our ocean biogeochemical models, and then I'll summarize that. So starting with observations. And what I'm showing here are transects of two different biogeochemical tracers in the ocean. The top one is nitrate. That is a nitrogen-based nutrient that is used for the basis of productivity. So that is necessary for life. It's part of plankton biomass. It's part of their cellular structure. It's part of their DNA. It's a necessary nutrient for growth. And then in the bottom panel is oxygen. A lot of what we have in our model are photosynthesizers in the ocean. They're called autotrophs. And they consume nutrients and release oxygen in the process, just like trees and plants do on land. Autotroph phytoplankton do that in the ocean. And they create dissolved oxygen gas in the seawater. And then it is remineralized back into oxygen when that is created. The oxygen is consumed when the organic matter from the productivity is remineralized, and I'll talk more about that. But so these are the two things that I'm showing. This is a transect in the Pacific Ocean. There's a delay. Is it showing up there? There we go. It's showing up there, but not on my screen, so I have to do this. So here is the location of the transect going from Antarctica up to the Bering Sea. And in the plot, this is going from the coast of Antarctica northward as you go from left to right up to the Bering Sea, and the vertical axis is depth. And these are the little dots that you can probably barely see are individual observations that lead to the color map as well as the contour lines. So some of the features, immediate features that you would notice is that in the surface waters, nitrate is low, particularly at mid to low latitudes. And that is because that is where primarily biological productivity happens and the nutrient is consumed. And so that biological productivity happens until there's no more nutrient available. So it's basically stripping the water of nutrient until there's none left. And that is what then ultimately limits how much biological productivity can happen, is how much nutrient is present in the euphotic zone. Light is required for that photosynthesis, and so that is why that process happens primarily in shallow parts of the ocean. It also happens more readily in warm waters because that speeds up biological processes, and so the mid to low latitudes, there's more effective consumption of the nutrient compared to higher latitudes where there's less light and it's colder. Once the critters grow, I'm just going to refer to the plankton as critters, loosely speaking. They are consuming nutrients and carbon. I'll show another plot in the next slide of dissolved inorganic carbon, which is going to exhibit some of these properties as well. The productivity consumes nutrients and inorganic carbon and produces the organic matter of the plankton and oxygen. What happens next in the life cycle of the plankton is that they either die through natural causes, just mortality, or they might viruses or bacterial infections of the plankton, or they get eaten by larger organisms like zooplankton, also called grazers, and then so on up the food chain until you get to fish in larger trophic levels. That organic matter then, then that is still remaining in organic matter when they die through natural causes. Some of that matter ultimately sinks as sinking particles through detritus or shells. There's some types of plankton that create calcium carbonate shells or silica shells. The calcifiers, coccolithophores is one type of calcifier, or diatoms is another class of organisms that make silica shells, which are really beautiful if you look at those with electron microscopes. In that sinking matter then redistributes that matter through the water column as it then remineralizes into organic forms. In that process of the organic matter sinking through the water column and being remineralized, for instance, by bacteria, leads to the enhanced, does the pointer work? Can you see that? Yeah, leads to enhanced values at mid depths where that sinking organic matter remineralizes back into the inorganic form. In that remineralization consumes oxygen. When the bacteria munch on the organic matter and break it down into an inorganic form, they use oxygen, and so that depletes oxygen, and that is why you have this low oxygen values that you see at mid-depth. Primarily, you see it at 40 north on this transect. So this is that remineralization of organic matter is adding back, it's sort of like the reverse of productivity, which is adding inorganic nutrients into the water column and consuming oxygen. And then just besides that sinking particles as a transport mechanism, that's called the biological pump, something you might have heard about. The general circulation of the ocean is also moving that organic matter and inorganic matter through the pathways through which parcels of water are moved through the ocean. So there's general circulation through advective transport. And so that primarily happens along this transect, that you get deep water formed at the Antarctic coast that then flows northward. And so this water is slowly moving northward, and as it moves north, when it was created at the surface, it's with these lower values of nitrate, and as it moves northward along these water pathways, the nutrient is remineralized into that water parcel, and the concentration increases as that water parcel moves away from the Antarctic coast. So that remineralization is adding generally nutrients to the water parcel and consuming oxygen as it gets farther, as the water parcel ages within the water column. So that's advective transport, and there's also then lateral and vertical mixing that move these constituents around in the ocean. So there's boundary layer mixing near the surface of the ocean that you've heard about through the previous talks this morning. And lateral mixing, stirring through eddies in submesoscale processes are also mixing biological constituents, primarily on isopycnals for the mesoscale eddies. And then for a smaller scale, it can be cross-isopycnal mixing. If that were the only thing going on, all of those processes, then you would expect that oxygen and nitrate to be nearly perfectly anti-correlated with each other, because these processes are just moving things around, and the biological processes are either consuming one and producing the other, or vice versa. But if you look carefully at these maps, they're not exactly the opposite of each other, particularly if you look at oxygen near the surface. What I said is that oxygen is produced where nitrate is consumed. You see that nitrate is really, really low here at 20 north, and you see that oxygen is kind of high, but it's higher farther north. Whoops, jumped ahead. And what's going on there is that oxygen is exchanged with the atmosphere at the air-sea interface. There is an air-sea exchange of many dissolved gases in the ocean. And what is particularly notable about that is that the atmosphere for oxygen is essentially an infinite reservoir, and it will bring the seawater into an equilibrium concentration of oxygen. And that equilibrium concentration of oxygen depends upon temperature. Colder water can hold more dissolved gas than warmer water. And so part of the deviation from the precise inverse relationship from nitrate and oxygen is because there's this temperature-dependent air-sea exchange going on with oxygen that is not going on with dissolved nutrients. And so you get large values of oxygen at high latitudes where the water is very cold and can hold a lot more oxygen. Now we're dealing with a model, the CESM, which a lot of CESM is focused on modeling the climate, and I'm going to use that C word even if we're not allowed to these days. And greenhouse gases are an important part of that. And carbon dioxide, the ocean regulates heavily the atmospheric concentration of carbon dioxide. The form of carbon dioxide in the ocean is primarily referred to as dissolved inorganic carbon. It's not just dissolved CO2 gas, because when CO2 gas dissolves into seawater, there's then interesting chemistry that happens there where the CO2 molecules chemically interact with the seawater and start forming other types of species of carbon in the ocean that are inorganic forms of carbon. There's carbonic acid, there's bicarbonate ions, there's carbonate ions that are constantly shifting amongst themselves through chemistry. If you add all of those up, that is referred to as dissolved inorganic carbon. Sometimes it's also called total inorganic carbon. And the ocean is a large reservoir of carbon in the climate system that is primarily stored in this dissolved inorganic carbon form. And so this is a similar transect to what I showed in the previous slides for nitrate and oxygen, and it has some characteristics of both of them, in that the productivity drives, in terms of productivity in biological processes, DIC is more nutrient-like, because when there's productivity and the organic matter is formed, that consumes DIC from the seawater into the cellular structure. And so there are many characteristics here, like the low values at the surface at low latitude because of biological productivity, and the higher values at intermediate depths. That is as a result of the biological processes that I was talking about with nutrients. But DIC also has characteristics where it behaves somewhat like oxygen, because DIC, through the CO2 aspect of it, has this temperature-dependent air-sea exchange. So you get elevated values at higher latitudes like you do for oxygen. So carbon, which is climatically relevant, has some aspects that start to behave like nutrients and some aspects that start to behave like dissolved oxygen. So these are the features that are present in these are the main features that are present. And I'll get to that I'm skipping a slide mentally, so sorry. That air-sea exchange of CO2, this is a map from circa year 2000, a climatological air-sea flux of carbon dioxide, this air-sea flux of carbon. And what this map is showing is through many observations of the partial pressure of dissolved carbon dioxide in the seawater, and then estimating what the flux is of carbon in and out of the ocean exchanged with the atmosphere. In these plots, red positive is CO2 going into the atmosphere, and the blue is carbon going into the ocean. And this is strongly dependent upon biological productivity signals, where the productivity happens that draws down carbon and then it is replenished through air-sea exchange. And so a lot of these blues that show up in this plot is where there's biological productivity. There's also a large thermal response, and that is primarily what's driving the outgassing in the equatorial Pacific, because there's upwelling of cold carbon-rich waters that when it hits the surface, it starts to warm up, and that reduces the capacity of that seawater to hold the carbon, and then it outgasses it because it is supersaturated once it warms up. And that is what leads to this low latitude outgassing. And so that thermal dependence of the exchange plus the biological productivity is what leads to this observed patterns of air-sea flux. And these are the sorts of things that we try to, the processes we put into our model and then see, do we capture the observed features. I'll restate this in words because some people like to see words in their lectures more than pictures. It helps different learning styles. So again, there's the biological productivity in the euphotic zone, consumes nutrients and inorganic carbon, produces organic matter and oxygen. That organic matter is exported out of the euphotic zone through sinking particles in the circulation of that suspended matter. That organic matter is remineralized back into inorganic forms. It's sort of the reverse of productivity, and that consumes oxygen. And there's general circulation, the advective transport and mixing through mesoscale in turbulent processes. These are the primary large-scale processes that are governing the distribution of the biogeochemical constituents in the ocean. If you look at very large-scale stuff, there's the temperature-dependent air-sea gas exchange as well. There are other processes that globally are not as significant, but regionally they can be considerably significant. One is atmospheric deposition of nutrients, such as iron, which is a micronutrient, which is necessary for biological life, as well as other nutrients that are deposited from dust from the atmosphere, like nitrate and phosphorus comes in through dust that is deposited on the ocean. So there's iron, nitrogen, and phosphorus. There's sediment burial. Some of those sinking particles reach the seafloor and are buried, and they are not then released back into the climate system until you're on very long geological timescales. There are riverine inputs often can be rich in nutrients from natural processes like weathering, nutrients that can come from terrestrial processes, as well as from agricultural inputs like fertilizer. And those can be very significant locally near river mouths. Other processes that are relevant locally is a process called nitrogen fixation. And this is the conversion of dissolved nitrogen gas N2, which is by itself typically not biologically available to microorganisms. They are not able to use that nutrient to grow because of the strong bonds. Chemically, N2 as a dissolved gas has very strong bonds that takes a lot of energy to break, and very few organisms are able to have the energy chemically to split that apart and then use it as a nutrient. Some can, and so those critters can survive well when there are not other nutrients present, other forms of nitrogen. They can then use the dissolved gas of nitrogen for their biological productivity. This is that conversion of dissolved N2 gas into ammonia. There's another process, denitrification, where the remineralization of organic matter, if that happens inside an area that is low in oxygen, these are places called oxygen minimum zones, then it will start to consume, when there's not enough oxygen to fuel that remineralization, there are organisms that will switch to consuming nitrate instead of oxygen. And so that converts the nitrate into other forms. This is particularly can affect the nitrogen cycle in these oxygen minimum zones. So now I'm going to get into some of the so those are the large-scale processes that we represent in our model. I'm going to get into some of the modeling that we do of biological productivity, or the types of models that we have. And there are, I'm sure you haven't seen enough acronyms yet in the lectures that you've heard, but one that shows up often in the biogeochemical modeling is NPZD models, where N stands for nutrients, and P is phytoplankton. These are the photosynthesizers. Z is the zooplankton, the grazers, the ones that eat the phytoplankton, and D is detritus, that dead organic matter. And the nutrient can be, in some simple models, you might just have one nutrient present, or you might have many nutrients present in your model. The types of nutrients that are often modeled in these would be nitrate or ammonium, which are types of nitrogen, phosphate, which is a form of a phosphorus ion, silicate, and iron, and other micronutrients. This is a diagram from a simple biogeochemistry model that was due to a researcher, Mike Fasham, that I pulled off a particular website that has a very simple model of a phytoplankton, PHY, that's the P, which in these arrows represent flows of matter from one part of the model to the other. And each circle represents a tracer or a pool of carbon or nutrient in this model. So the phytoplankton, there are processes where when the phytoplankton die or are grazed, the matter from them goes into the detritus in the upper right. I'll try this pointer again. Whoops, don't click. I can't find my cursor. Aha, there it is. The phytoplankton, when they graze, are converted into zooplankton, or when they are ingested, or they die, they might go into detritus. The bacteria also can die into those forms. And the bacteria can graze on the detritus and converting that into a dissolved organic form, the DON, dissolved organic nitrogen, and also into the ammonium. And this doesn't really show the sinking particles, but the zooplankton can decay into DON and ammonium, and there's also arrows from the phytoplankton for mortality into the DON and ammonium. And then all of this is fueled by nitrate, the nutrient that fuels this. This is a relatively simple model that this diagram is depicting. But now I'm going to show you some equations of an even simpler model that just has 3 pools in it, a simple NPZ model. And just to show you how complicated the equations can get, if you just have 3 pools, this is an example of what the equations look like. So this is plankton is the top row, and the time evolving part, the derivative, the change of plankton depends upon, I lost my cursor again. There it is. This big term here is growth, photosynthesis. So it is proportional to the concentration of the phytoplankton. There's a term here where E is available light, and there's a variety of parameters that describe how the productivity is limited by light with this particular functional form. There's a limitation term from nutrients. This is called a Michaelis-Menten form or monad for the limitation due to nutrients of productivity. And then there's a optimal growth rate, mu naught. There's a loss term, which is from grazing, which depends upon how much plankton is available, and it's proportional to the zooplankton. And then there's a coefficient out front that I'll mention, what is a grazing rate. And then there's a mortality term that they're just assumed in this model to die at a linear rate. The grazing is consumed when they're grazed, the plankton go into the zooplankton, but if you look carefully, this term here is almost the same as this, but there's an extra coefficient out front called A. And that is because when the zooplankton are munching on a phytoplankton, they don't actually ingest all of it. Some of it is not consumed, it is not ingested, it goes out back into the nutrient pool and stays in the seawater. In this A is the ingestion fraction of the grazing. And if you look over here, the rest of that grazing goes into the organic pool. So this grazing term goes into the zooplankton and to the nutrient pool. And then there's a mortality loss term for the zooplankton as well, the last term on that zooplankton equation. And then each of the other terms, the growth term of plankton is a loss term for the nutrient. The mortality term for plankton and for the zooplankton are gain terms for the nutrient. So there's this three coupled ordinary differential equations, and there's mass conservation. Everything that comes out of one pool goes somewhere else. But even that simple equation has with just three pools, has about a dozen different parameters that you need to estimate to come up with your model. And in our more complicated models, you can imagine, many, many more parameters in your equation. We can easily have over 100 parameters in our full-blown biogeochemistry model for CESM. So how do we estimate those? Some are done from laboratory and field incubation experiments where you look at photosynthesis or radiance curves to look at how the autotrophs respond to available light, to get the coefficients in that light curve. You look at what happens when you put them into a container and add nutrient and see how much their growth responds to that. You look at grazing rates by putting grazers and phytoplankton into incubators, and you see how rapidly the phytoplankton are consumed by the grazers. You can come up with estimates of these coefficients from experiments as well as going out to sea. Then you can also, sometimes there's a lot of uncertainty in those parameters, and then you can tune and adjust the parameters to better match overall observations of these fields. And sometimes we just use the values that were used for coefficients in previous models instead of restarting from scratch. And that is where a lot of our parameters come, because a lot of research has been done over the years to establish appropriate values, and we carry on with using those older values. Instead of representing, there are thousands and thousands of types of plankton in the ocean. We cannot model all of the individual species in the ocean. We need to put them into categories, much like is done for the land model. Have you had the land lecture yet? So you've probably heard of PFTs, called plant functional types. PFTs here means plankton functional types, which is groupings, and I don't know who coined the acronym first, honest, I don't know. But for the ocean with PFTs, these are plankton functional types where we categorize the plankton into categories based upon how their geographical distribution is, or the biological role that they play in the system, like they are calcifiers. And so we group all the calcifying organisms into one type of plankton functional type, or the silicifiers, the diatoms that make silica shells, or the diazotrophs, the ones that can fix that N2 dissolved gas into ammonium. Those biogeochemical features, we put all the species that do that into one box, even though there are many, many species that can do those processes, because we can't put all of them into our model. So once you start doing this categorization, different modeling groups start to maybe split some of those groups up into two types of groups. You might have the small phytoplankton and the large phytoplankton, or you do subdivision of those plankton functional groups. And there are varying levels of complexity in these models. And then you can start to ask the question, well, which one's best? Which one should I use for my research project? And there's a really nice paper by Friedrichs et al. From 2007 that started looking at this with a dozen different models of varying levels of complexity and asking the question of basically which model is the best. And they compared these 12 different models at how they performed at two different sites. In these plots here, EP is the red, is equatorial Pacific, and AS is the Arabian Sea, two very different biogeochemical regimes in the ocean. And in these plots, a high bar is a cost, so that is a poorly performing model. So what Friedrichs did was she got models from 12 different researchers and ran them at these 12 12 different models at these 2 different sites and see, well, how well did they do? And the performance was really all over the map, and she just took their default parameters. And one thing you can see here is that, and these are arranged in order of increasing complexity, going from left to right. And the more, if you look in that first panel, the untuned models, the more complex models did better. But then Friedrichs retuned the parameters to try to do better at both locations. And when she did that, she found that there really was not much benefit of having the additional complexity. That's in the top right, where she tuned it for the equatorial Pacific and separately for the Arabian Sea, individual settings of parameters. If you tune your model to work in one particular site, the low complexity model did just as well as the high complexity model. But then, what if you try to tune for both locations simultaneously? And that's in the bottom left. When you're trying to handle different regimes simultaneously with one parameter set, the high complexity models did better. So there was a benefit for using a more complex model if you're trying to capture different biogeochemical regimes. That happens when you're doing global ocean biogeochemical modeling. If you're just doing regional modeling in one ecosystem, not so much. But for global modeling, the high complexity model gives you a benefit. And then the final panel is showing what if you take it and apply it, tune it from one setting, and then apply it to the other setting without retuning it. If you take the best settings for the equatorial Pacific and run it in the Arabian Sea, how does it do? And this is what happens when we tune our models for the few places where we have good observations, and then we run it globally, we're going to be running it in regimes that the model was not tuned for. And so this bottom right panel is sort of saying, well, how does complexity help you with model skill in regimes that you have not tuned it for? And what you see here is that the high complexity models give you a benefit when you apply it to a regime that it was not tuned for. And this applies for biogeochemical regimes that you didn't tune for, or past or future climates that you have not tuned for, that we don't have observations. If you've got observations of the future, that'd be really cool. But so there's some take-home messages from this Friedrichs paper is that the question of what is the best model depends upon your application. If you're doing a regional model, you can get away with a low complexity model because you can tune it really well for that region. If you're trying to do future projections where you're going to change the biogeochemical regime that you're trying to capture, you're going to need to use a more sophisticated model to have some confidence that your future predictions are going to be relevant. So there's not a single answer to what is the best model. The answer is it depends upon what you're using it for. Hopefully you've learned that with a lot of the other stuff that you've been learning through this tutorial. In CESM, we have a model called MARBLE, which stands for the Marine Biogeochemistry Library. And the main features of the MARBLE model in CESM3 are we have various nutrients, 2 types of nitrogen nutrients, phosphorus, silica, and iron. We have 6 plankton functional groups. There's 4 that are autotrophs, that are the photosynthesizers, and 2 grazers. Sometimes this is referred to as a 4P2Z model because of that. One of those autotroph types is explicit calcifiers. That's a new feature in CESM3 that we didn't have previously in CESM2 or CESM1. So the model's we've gone more and more to the more complex model as we have enhanced the model. And there are 41 biogeochemical tracers related to the biogeochemistry in CESM3, which is many more than we've had in previous versions of the model. From 32 to 27 to 24 in previous versions of CESM. In the autotrophs, in the phytoplankton, there are variable ratios of nitrogen to carbon, phosphorus, iron, silica, and chlorophyll. And in previous versions, some of those were fixed. And so that is improving the skill of the model, but adds more tracers makes it a more expensive model. We also have what's called an iron binding ligand, which helps with the skill of the iron model, which I'm really not going to go into because of time. This is a diagram of the processes and the pools of biogeochemical constituents that we have in CESM, where the arrows are showing where the matter flows from one class of pools into another. So we've got these types of phytoplankton where we have a small phytoplankton, the pico and nano calcifiers make the calcium carbonate shells, the diazotrophs that fix nitrogen gas, and the diatoms that make silica shells. They consume nutrients and make oxygen, which are in this bottom left pool. And they are grazed into the zooplankton, the top right pool. We have two size classes of zooplankton. And then there's dissolved inorganic matter, detritus, and there's a sinking particle, which is not an explicit tracer, but is instantly redistributed throughout the column in our model. And these are, if you go back to these slides, here are some references that describe various generations of the marble model used in CESM through various versions of CESM. 2 minutes, okay. Some of the major gaps in our model are some of the features that we don't have. Our riverine inputs of BGC tracers are prescribed from data sets. We are not coupled to the land model. The stuff that is buried in the sediments is lost from the system, and we do not have any treatment of biogeochemistry in the sea ice. And we have desires to do all of these things in the future, but they're not present in CESM3. And historically, this model is based on the lower trophic levels of the biological productivity and the carbon sink in the ocean, though there are some options to couple our output to a fish model called Feisty. I'm going to speed up. Some of the things that we measure our model against to assess the skill is observing observed nutrient distributions of phosphorus, nitrate, and silicate and oxygen from global databases, comparing DIC in a related quantity alkalinity to observational compilations called GLODAP, compared to satellite measured chlorophyll and productivity, and CO2 fluxes. And this is an example of comparing the air-sea CO2 flux in the model in the top panel to a neural net derived CO2 flux product that is based upon observations and then filled in with a neural net. And there's a large scale resemblance between the model and the observation-based product. Those are annual means there. And then in the middle panel is showing a seasonal cycle with the zonal mean, and the right shows the zonal mean of the annual mean. So you can see that the model and the obs are close to each other. There are a lot of challenges in doing this modeling. I mentioned that we have many, many parameters, and determining what the appropriate values for the parameters. There's a lot of uncertainty in those parameters. When you group different species together, that adds a lot of uncertainty to it. And then we also have biases in our model of circulation that sometimes we don't want to if the model doesn't look right for the biogeochemistry, you have to decide, is that because we have the wrong parameter, or is that because the circulation has a bias? And it's tricky to figure out, decipher and disentangle the source of the error to see how should you set those parameters. And also, initializing the model is a complicated thing to do as well. So in summary, there's these large-scale biogeochemical features that I showed in the very first slide. They're determined by a handful of processes. We include those processes in our models. We have a particular class of model to deal with the science that we try to do within CESM, but there's other models that are appropriate for other applications. And the questions that you're trying to answer with your model guide what sort of model you would use. And then an advertisement in the practical session, there's going to be one on coupled carbon cycle modeling on Friday's session for the practical exercises. And that feature is still under development for CESM3, so that's not available in the version that you are using in your tutorial exercises. So there's an exercise related to the coupled carbon cycle that is using a version of CESM 2.1. So I'll just give you a heads up about that. The development for the coupled carbon cycle is still in progress for CESM 3. So that's my content. Thank you. Oh, and I should say, if you want to look back at the slides and look further, there are multiple extra slides that deal with the coupled carbon cycle that I knew I would not have time for, and I moved those into the extra slides. So if you want to learn more about that, there's plenty of extra slides about the coupled carbon cycle in previous versions of the model, as well as a lot of literature references that if you want to delve into the research on the carbon cycle and Earth system models, I have a variety of references to help give you things to look at in the future. Questions? Yes?
Thank you so much for that. I have two questions. The first of them being, I was wondering if there is a seasonality to, the dissolved nutrients on like a global scale, or if that's also more of a regional thing, or if the seasonal variability is not that high.
There's absolutely a large seasonal cycle, and there are a number of processes that lead to that seasonality. At the top of the list is light, because light is needed for photosynthesis. And so there's a seasonal cycle to the distribution of light, particularly at mid and high latitudes. At the high latitudes, it's there's not going to be any productivity in the Arctic Ocean in the winter. There's no light there. And in the mid latitudes, there's less light in the winter than in the summertime. There's less of a seasonal cycle at low latitudes, but light's the top of the list. And then another is vertical mixing, which has a strong seasonal cycle. So the vertical mixing is a supply route of nutrients, nutrients that have remineralized at depth. When you get deep winter mixing, that replenishes nutrients in the euphotic zone to fuel it for the subsequent spring. And so that vertical mixing, the deepest vertical mixing happens in the winter when you get cold, dense waters that are formed from cooling the seawater to the atmosphere, heat going into the atmosphere, and that replenishes the nutrients through vertical exchange. So those are two of the big processes that lead to then a large seasonal cycle in biological productivity, and then nutrients as well as organic matter. Sure.
My second question was, just out of curiosity, how are the dynamics of, and I mean kinematic dynamics, like how the phytoplankton and stuff move around, is that very much dependent on just the general circulation of the ocean, and are smaller scale turbulent flows very important to that? Or if it's more of a large scale circulation thing that you
Both are, well, in the model, all of the processes that transport heat and salt are applied to the biological tracers. So the large-scale circulation is applied, and the small-scale turbulence, particularly, say, vertical mixing, the diapycnal mixing in a turbulent boundary layer, is also applied. So all of these, in mesoscale mixing from the mesoscale eddies that are tens of kilometers in size, all of those processes that lead to transport of matter are applied to all of the biogeochemical tracers in our model. In all of them matter to the biology. Absolutely.
Are they often parameterized, or are they treated differently depending on the resolution of the ocean model itself?
The processes, particularly the large-scale circulation is effective transport is a resolved process, so that is not itself parameterized. But once you start getting, there are the effect of mesoscale eddies in the coarser models is parameterized through mesoscale mixing, as well as a parameterization called Gent-McWilliams transport that I think was probably spoken about by Peter in the back earlier. And the turbulent mixing that happens in the boundary layer, as well as things like internal waves in the interior of the ocean, that's all parameterized. In the same parameterizations that are applied to heat and salt are applied to the biogeochemical constituents. One thing we don't have in our model that happens in the real world is that the plankton and zooplankton in our model don't move on their own. So they are just transported by these processes, whereas zooplankton in reality move vertically themselves out of their own propulsion. I mean, they'll move their, I'm forgetting the term for it, but they have vertical migration, and we have projects that people trying to do diurnal migration of zooplankton They go to deeper depths when it is light to avoid predators. And we don't have that in our model, so that would be something that is applied to the plankton that is not applied to heat and temperature. But at this point in our model, the same transport processes are applied to the physical variables as are applied to the biogeochemical variables. Yes?
Can we say that ENSO is the most important modulator for the ocean carbon cycle?
Depends upon what you're looking at. I think the answer is, just like is there a best model? The answer is it depends upon your application. If you care about the effect of interannual variability, how the ocean contributes to interannual variability of atmospheric CO2 concentrations, then ENSO would be the biggest driver of that. If you're looking at longer time scales, then you'd have a different answer. Maybe the PDO or the AMO on longer time scales would be more relevant, as well as just the solubility pump of increasing CO2 in the atmosphere. Is that just, there's a solubility pump of that into the ocean, which is primarily governed by chemical processes and not necessarily variability. If you then, that's for global scale, if you're looking at the result of the effect of ocean carbon on the atmospheric CO2. But if you're looking more locally, like if you're looking at a coastal place, then maybe riverine processes, riverine deposits into the ocean are going to be more relevant. So it depends upon the spatial and temporal scales. So if you look at the one particular spatial and temporal scale, yes, El Nino is the most important. But for other spatial and temporal scales, that's not going to be the case. It depends.
Hey, maybe Keith can stay for a few minutes during the next break?
Yes.
Okay, great. If we want to continue the discussions. Now we're going to have a break until 2:15. Come back in here for a quick check-in about the lab, and then we'll go back up to the library. And let's thank Keith one more time.
I kept seeing it, I was like, oh, I don't want to kick, I don't want to kick that.
Do you want to get the check-in? Yeah, you have something to say. Yeah, that's great. I'm going to put more cup on the...
Hello? Okay. Oh yeah, you did add it. Yeah, I just added questions about it. It's just, yeah, quick stuff.
Yeah, let me just... Okay, then, yeah, I want just to check in if everything, you have burning question about the lab that you are comfortable to share with everybody. Otherwise, I can answer private question in the room. Sometimes people are afraid to ask a silly question, which there are no silly question, but then this is one thing that people ask me about. Then I want to clarify a little bit hybrid versus branch, because people seems they are confused what they should do. And me, I think it's a no-brainer. You should do hybrid. I always do hybrid. Then basically the difference between the two. Let's say you do a 10-year control run. It's called a startup. You just do a 10-year run. Now, if you start the run exactly the same way, everything is the same, name lists are the same, everything is the same except the name. You do a startup, you do 5 years, and then you continue the run for another 5 years. It's what we call a continue run. And if you do at the end the data of this run compared to the first one you did, they will be bit for bit, they will be exactly the same, it's the same run. This is the first thing. Then it's what we call a continue run. Then now, why would you want to do a branch? I think the only time I do a branch, I never do branch basically, but I do sometimes branch, if I want somebody, let's say I run a 2,000-year simulation, and then I have a colleague who loves to look at diurnal cycle of precipitation. It's called Rich Neal. And then he would like to have like 3-hour precipitation. I'm not going to output 3-hourly precipitation for 2,000 years. Then I'm going to do my run, and then at some point I will do a branch where I will output for, let's say, 20 years of 3-hourly precipitation. And the branch, it starts in a very sophisticated way to make sure you are bit for bit. As your first run, you are just continue the run. And if I do a branch, I will be bit for bit. And you want to do this because, I just want to extra output. I don't want to change anything in my run. I want to have more data, more variable, or I forgot to output temperature, for example, drama, then I can do a branch. But now, in most of the case, you want to do an hybrid. Why do you want to do an hybrid? It's that when you do very long run, the model is spinning up. You start from observation, and then it's going to spin up very slowly, especially the ocean. The atmosphere is going to spin up within 2 weeks. The land, maybe it's going to take a couple of decades. The ocean, it's going to take a very long time to spin up. Then you want to do, in this case, a branch run that will start from, let's say I have done this very long run, and then I'm going to start an hybrid here that will use the restart file. But then this is not bit for bit, because the way you start is a little bit different, but it's much more flexible. For example, if you do a branch run, you cannot change the start date. It's very constrained. A branch run, you can run you can use the initial file, the state of the climate model that you have at the end of another run, and use this to start. Does it clarify a little bit? I don't know what you were told before between branch and, yes. Wait a minute, do I need to give the microphone or? Okay, yeah, then you can.
We subtract variables as well, just so the output is a little faster. Like I know we can add more variables, but can we
Yeah.
also like
Okay.
remove variables in?
Yes, there is, in the lab I show something that's called Finkel, F-I-N-C-L, and otherwise there is like a variable that's CL exclude. Then you can remove variable if you don't want to do this. You can even do better than this. Me, I want to output when I do all my development run that I was showing on the first day. I want just to output a small set of variable. What I do, I remove all the output. There is a Namelist variable. I'm always talking about the atmosphere, but there is a variable that's called empty tape. Then you can remove all the output and just like put the 3 variables you want to look at. Sorry?
Is that true for both branch and hybrid?
Yes, yeah. Any more question? Do you want to do another row? No, I'm kidding. Okay. Yeah, this is about the tutorial queue. Then I'm reading the slide with you because I didn't put up this slide. Then the tutorial queue is a special queue that they give you during this week. Then you can bypass everybody. It's like when you go to Disneyland and you have like this bracelet and you can pass the line. It's what you are doing right now. All the people here at the building, they hate you. Then just like, no, I'm kidding, they love you. But it's just like you are going in front of everybody. But at Friday at 5 p.m., this is it. You are becoming regular citizen like everybody else. Then good luck with that. There is like the project tutorial. It seems it's going to be available until August 31. Does it mean they will keep their account until August 31? Or? Yeah, then probably they will be empty. If something grab it over the weekend, it's not like a lot of hours, but if there is hour, please feel free, but don't go crazy to run your PhD thesis on it. Then. And then porting, it's not yet supported for CSM3, it's still in development, but if you want to port, we had a discussion with a young man, I don't see him in the room, but I talked with Brian Dobbins, and it seems that if you need help to port, and if you can give him an account to your computer, he can port the model in 2 hours, he say. Then it's pretty good. If you do it yourself, I port the model to another institution. In Sweden, it took me like 2 weeks. But yeah, but it was a long time ago. It was not as convenient as now, but still 2 hours ago. Then, otherwise, if he say he can help with this. Then port him CSM2 refer, yeah, then. But I can put the address of Brian Dobbins because he said that he would help. Okay, and then, okay, then this I don't know. Yeah.
Just another reminder that after our PM, this next lab session, come back in here. We'll have a quick check-in. Elizabeth will send out that daily survey, and the raffle's happening on Friday. So just remember to fill out your surveys. And yeah, unless anyone has other questions, we can head up to the library.